So what I'm going to do today is tell you about an application of some ideas that I've talked about in the past that we have developed in the area of semantic information processing, extracting information from spoken language. And an outline of the talk that I'm going to give today is I'm going to start out recalling some motivation for why AT&T, and I in particular, am interested in doing things like this. Why would a telephone company be interested in questions like that? Then I'm going to give a 3 or 4 slide reminder of the work that I talked about for an hour and a half last time, which is the theory and practice of semantic information processing. And I decided not to repeat that because that would bore Fred anyway, who heard it before. And go on and talk about a new application that we've been working on to AT&T customer care. Okay, understanding things that people say to AT&T customer care agents. Right? And as many of you remember, in the past, we had spent a few years looking at the type of things that people say to AT&T operators. An operator you talk to when you want to make a phone call or a collect call or put it on your credit card, or you have questions about making a call. A customer care agent, be it from a telephone company or a bank, you're talking to about questions about your bill and the plan, by which we charge you. Is it 5 cents a minute or 7 cents a minute? And the whole domain is intuitively a lot more complicated. And one of the things that came out of this last year of work, which I find kind of interesting and like to share with you and get feedback on, are thoughts that we've developed on how do you quantify notions of the complexity of a spoken language understanding task. That seems like something that's important. I'll show you some stabs that we've made at it, but it's by far all means not done. And then I'll talk about some experimental results, both in batch mode and in dialogue systems. And I'll play you some examples at the end, after Andreas is gone, of people actually having a dialogue with our machine. And these are real live people. Okay. So motivation. If you call up any large organization today, you almost never get a person unless you're a gold or a platinum customer. And what you get is a machine, which gives you a menu. Now, everybody knows who Alexander Graham Bell was. He was the guy who invented the telephone, and the first words spoken over the telephone were, "Mr. Watson, come here, I need you," because Mr. Watson was his technician in the other room. And if Mr. Bell wanted to do that today, he'd get a menu like this. Okay, so I like this one, and I collect cartoons and Seinfeld clips, if you remember Kramer, playing with menus. And Fred told me 15 minutes worth of stories over lunch about his horrible experiences with menus. So we'd really like to get away with menus, get away from menus. Why are they there anyway? Are they put there by large corporations and government agencies just to torture you and to keep us in our place? And the answer is no, even though you might feel that way. What happens is to have a casual conversation with a customer, with some kind of customer care agent, whether it's us or any other large organization, will cost about $5, okay, of resources. Well, if you spend, $1,000 a month with us, fine, we'll talk to you all you want. But, most people don't spend that much, so what do? Do you charge for it like you do with directory assistants? Or do you introduce automation? Companies have introduced automation. Menus are okay in their place. If you have a menu that says, please say collect calling card, or person to person, that's fine because everybody knows what those things mean. If you have many of the menus that are out there now, they're not okay. So our motivation for many years has been how do we provide automated customer services over the telephone by natural spoken dialogue, and for us, natural means what people really say. Okay, so you've all seen and played with systems where if you can type English sentences or speak English sentences, and if you say the right words in the right order, it will be an English sentence or some other natural language sentence and it will work, but if you deviate slightly, it'll die. If you think back to the ATIS task that many of you are familiar with, for those of you who remember that database and that government-sponsored task, they classified the sentences into Class A, Class B, Class C, Class D, and Class X, which are the ones that they just totally excluded. That, I'm told, was 30% of the database. because those weren't fair to say to the machine. If you're an AT&T with 80 million going on 70 million customers, you need to just take what people say, and you can't tell them that they're not talking right. So now let me move on and say a few words just to remind you of the way we think about this. For those of you who are interested in more details, you can see my videotape from 3 years ago, or go to our project webpage at research.att.com. Okay, and the idea is that our goal here is to extract meaning from speech. And what does that mean, is the question. Well, this is the primary thing that we're interested in. And in order to think about this, we have to understand how to quantify the information content that's in a natural language message and how much of it we can extract. And if you want to build and engineer machines and understand the limitations, we need to think about such things. Now, there is a science called information theory, but let me spend a minute on the communication paradigm here. Here, the communication paradigm is I want to talk to the machine and get it to do something, to make a call, to answer a question for me. I want it to do something, or maybe undergo some internal transformation, change a database. And if the machine responds appropriately, then it understood. Okay, there's not a necessary exactly right answer, but there's an appropriate answer. And we want to contrast this with traditional communication theory. And if you look at the preface of any of your communication or information theory textbooks, there's something along the line of this, which is the second paragraph from Shannon's original paper, which says, hey, the job of communications theory here is to replicate the bits. They might mean something, but it was pointed out to me that 50 years ago, you never said the words AT&T and wiretapping or listening into your phone in the same sentence. So, they might mean something, but those are totally irrelevant to the problem of replicating the bit sequence at the other end. Here, when we're talking about talking to a machine, I'm actually not interested particularly in which words you said. I'm interested in what it is you wanted, so I can do that for you.
He, of course, corrected himself. And
yes.
Created the theory of information with a fidelity criteria.
Absolutely, absolutely. Yeah, and one could actually carry it a step further, and if you look in the the collection of papers in his book, there's actually some articles that start saying, we really want to create a theory and algorithms for talking about the mutual information between what I say and what I want. So rather than the information of just replicating the bits, the mutual information between the bits in the original message and some action that I want the machine to perform. Okay? And there are thoughts along those lines. And of course, like all great ideas, it starts out somewhere, and then it turns out to be good for lots and lots of things, and that's exactly what we do. Right? So what we look at are mutual informations between things that people say and things that they want the machine to do. Now, I'm not going to spend a lot of time reviewing all those ideas and techniques because I've talked about it extensively in the past. And basically, this notion of mutual information, since it takes too long to say all that, we compressed it down in the spirit of Lempel-Ziv and just call it salience. Right? And what this does is it quantifies the notion that for a particular task, for a particular set of things that I want the machine to do, some words or linguistic events will be very important, and some not. Some will be more informative, some less. We have algorithms that look at corpora of what people say together with what they wanted the machine to do, and automatically acquires what are the salient words. Phrases have more information than words. The semantics is sharper. And then when you get a proliferation of phrases, which are minor variations of each other, we've introduced and talked about algorithms over the years to cluster these things. When you get a cluster of phrases, you can either represent it as a set of strings, and for those of you who were at this morning's lecture on FSMs, know that if you're at AT&T, you would never represent it as a cluster of strings. You would compactify, determinize, minimize, and everything else, and represent it as a graph. Okay, so.
What did you say to me? Bravo.
Okay, see, it was good that I came this morning. So, for example, for the customer care domain, that I'm going to talk about. So these are people calling up with questions about their bill. One of the common questions that people call up about is, there's this phone call here and I don't recognize this phone number or this place and I don't know anybody there and who is this? And if I don't know who it is, take it off my bill. Well, a salient grammar fragment that gets automatically acquired from the corpus is something like this, which contains variants. So one phrase through that is calls we don't understand, or calls I did not make, et cetera, et cetera. So these are variations on the theme, and we end up with hundreds of these salient grammar fragments. And again, the theory and algorithms of how to do this we've talked about in the past, so I won't go into detail on today. Things that we've done with these ideas over the last decade or so was, those of you who remember me from way back, remember in the late 80s, I was playing with a thing called a department store call router. So there were a department store. I don't know if J.C. Penney's is still in existence, but at the time we called it the J.C. Bell department store. Okay, because we were in Bell Labs back when AT&T was one company and J.C. Penney was down the road, et cetera. And it had a furniture, clothing, and hardware department. And the idea is if you asked to buy a sweater, it would send you to clothing. If you wanted a hammer and nails, it would send you to hardware. If you wanted a chair, it would send you to furniture. And I actually found an old tape in my basement with an audio clip from that system, dated March '91. So I figured I'd play it for you to show where we were 10 years ago. Now, who here knows what an étagère is?
Wait, what?
An étagère? It's a piece of furniture.
Étagère.
Étagère. I'm sure I pronounced it badly. Okay, it's this knick-knack shelf that my mother had in the corner of the dining room. That's right. And roughly a dozen years ago, she typed it into the system, so I decided to preserve it for posterity. And let's see if I can get this mouse thing to work. Okay, so this is about a decade old.
Hello, this is the J.C. Bell department store. How may I help you?
Do you sell étagères?
I will connect you to the furniture department.
Okay.
Please hold on. I am connecting you to the furniture department.
Okay, so we had all sorts of fun with this, and it did online learning and other fancy things. Jim Flanagan's reaction afterwards was very, very interesting, but 3 actions? Come on now, 3? And he wrote a note to me, which I enshrined in my scrapbook, that said, how about 1,000? So we then went on and looked at a sequence of tasks where you can ask 20 questions about the 50 states, on airline travel, on a multimodal blocks world where you have ideas of salience between visual and audio channels. Okay. And then there's a gap between 93 and 95, because in 94 I went off and spent the year on ATR, at ATR on sabbatical, thought about what I wanted to do next, and I said, we've been building these ever more complicated toys in the lab, and all these ideas seem to work. Well, this is AT&T. I think I can get some real data, tons of it, and we went out and got data on what people said to AT&T operators. Okay, so if you dialed 0, you got an operator who said, AT&T, how may I help you? And then you said something, okay? And we spent a number of years working on that. And what we found was that although people say lots of things, they were asking most of the time for about 15 different things. And then there was a tail to the distribution, which we called other. So it was a multi-class plus rejection problem. And we've been using that as a vehicle for a number of years for our algorithm research. Now, AT&T, being a big company, of course said, well, that's great, but, and they came to me about a year ago and said, how about, could you try for us customer care, which is the number on your AT&T long distance bill? Okay, and to put it in perspective, AT&T spends about $1 billion a year answering the telephone, okay, which is a lot. And, can you do something about that?
Maybe $1 billion not answer.
Well, yeah, that's the issue. That's the issue. So the next slide, I'm going to start talking about what this task is about. And the question that we posed was, can I just do call classification? Okay, just like we did before. Can I figure out which of, in this case, 19 different things you wanted? And for some of those things, we have automation in place, like unrecognized number. There's a menu somewhere that says, please touch tone in the number that you don't recognize, looks it up in the database, plays it back to you. Other things like I want to sign up for AT&T local service, there's no automation, but we can send you to a rep who specializes in doing that. So we're looking at it as a call routing function. Okay. Now, what happens today?
While we're at this, I mean, they send you to a rep, and then they say the rep is busy, the estimated time before it comes to you, 10 minutes,
Yeah.
or whatever. Now, this happened to me yesterday in this complaint call, all right?
But that was to the IRS.
That was the IRS.
Okay, wasn't our fault.
No, but they probably have your technology. Which is
That's true, yeah.
okay.
No, but it's not ours anymore. We left it with Lucent.
No, but you know, they said 10 minutes,
Uh-huh.
and actually within half a minute, the person replied. So,
I guess they were trying to get you to go away. And enough people listened to that 10-minute message and hung up that you got to where you wanted to go in a half a minute. Yeah. And it's an estimate.
Is there an actual, they see how many people are...
Yeah, they see how many people and they do an analysis and generate a projection. And that's actually a useful feature. This way you can decide if you want to hang on or call back later.
Next time it will be 20 minutes.
Wow.
See how we can hang on.
Right, so this is what we want to do away with. This is what we want to do away with. All right? So let me play you some examples of what customers say to a rep when they get to a rep, if they go directly there, and the rep says, how may I help you? And we actually did a data collection at the beginning of the year of 10,000 interactions between customers and reps, okay, and analyzed both the utterances, the language, and the dialogues. Okay, so here, okay, so one question that people call up about is about their account balance.
Yes, I'm calling regarding my bill. I just wanted to make sure that you received my payment.
Okay, so that's one type of thing that people say. Is that as loud as it goes?
Yeah,
That's as loud as it goes?
that's pretty
Yeah, okay.
We heard.
You heard it. Okay. There are some things that don't fit into any of the categories.
I want to know what's going on with these lines. I mean, I've tried yesterday to get out, and they told me that the circuits were all busy. Come to find out, there was a broken, the new type of line they put in there was cut, and they wouldn't have service till midnight.
Okay, so that goes on for a while. That's what we call other. You would just send that directly to a person. Okay. Now, one of the interesting things that we found in customer care domain is that people don't get to the point immediately. It seems to be a social thing. For operator services, people get to the point. For customer care, they start out, dancing around the problem, and then you have to have a dialogue to get more specific, probably because they can't even articulate what it is that's bothering them. So you get things like,
Hi, I have a question on our AT&T or our bill.
okay, I have a question about my bill. So that tells me that it's not a I'm moving, change my address question. So it does have some bits of information in it, but nowhere near as many as I would like. Another very common area is you've all seen these marketing campaigns for rates and calling plan.
But I don't know why you want.
I'm an AT&T customer, and I would like to know how to get the 7 cents a minute deal.
Okay, you got a question?
No, I was just saying, actually, I do the same thing, and I wouldn't think it's out of social something.
No.
I'm feeling that when I feel that when I tell you it's about the bill, that you will now bring up the bill on your,
Right,
on
exactly.
your screen. So
Yeah,
I'm
right.
giving you...
This is a perfect...
So I'm really getting down to the point that I...
That's right, yeah. And then we have some more dialogue. So the point that I wanted to make was that even for call classification, to get down to one of the things that I can actually do for you, there turns out to be dialogue involved. Okay, and I'll show you some dialogue trajectory analyses later that sort of say, yeah, a lot of people do exactly what you do, whether they're talking to a human or a machine, You're not going to radically change their behavior. That's the way people are. It's a user interface issue. The last one is something like,
I would like to report that we are moving.
okay, so somebody's moving. So the reason I played those for you is I want to give you a feeling that this is fluent speech over the telephone. It's not read, it's not dictated, it's not necessarily grammatically correct. It's all different speakers, all different channels. So it's a tough problem in both speech recognition and natural language understanding. Okay? Now, what I have here is a view graph design especially for Fred. Okay? Because he always says, you guys are going to find a way of making life less convenient for the customers. So first comment that I want to make is, remember I said to you, if we have a conversation with you, it'll cost us about $5 or $6. So we could charge you, and that's why you get charged for directory assistance. And even nowadays, if you call up Verizon or AT&T and you ask what's the area code for Baltimore, they send you to directory assistance and charge you for it now. Okay, outrageous, because it costs money to talk to people. So what companies have done over the past decade is spend years and years engineering these menu systems. Okay, and what I have on the left here is actually a transaction with the existing deployed menu system as of a few months ago. That if you had a question about, I don't recognize this number on my bill, so you wanted to get up to what's called the reverse directory. So in menu land, first you have to wander your way through, figure out, aha, this is where I want to be, and then from there it's really very easy, if only you could find it. Okay? And you'll bear with me for a minute as we walk through the big thing, and then I'll show you what it sounds like now with How May I Help You? Okay? And even Fred will have to acknowledge that this is an improvement.
For the time being, they didn't figure out how to screw it up. Yeah.
Well, that's because I've been sitting in all their meetings and yelling at them whenever they try. Okay, and what will happen is your call comes in. The first thing we do with your call is we have a caller ID, automatic number identification. We look you up in a database, and then the network asks you some questions up in the cloud. Then it routes you to some premises. We play you an announcement about, oh, if you're calling about your Verizon bill, go call them, don't bother us. And then, you know, let's check and make sure that we really know who you are and that you're not calling about your bill from your mother's house. And then you get to a menu, and then you get to a sub-menu, and then finally at the end, okay? So this is for your entertainment.
AT&T. Thank you for calling AT&T, your long-distance, wireless, and internet access company. For assistance with AT&T service, billing, or charges, or to report a move, press 1. To sign up for AT&T calling plans or for sales assistance, press 2. For specific AT&T products such as calling cards, Easy Reach 800, wireless, or WorldNet, press 3. To hear this information again, press 7.
Okay, so now we got through this.
This system can be used to answer your questions about services provided by AT&T. If you are calling about local service provided by any other company, please call that company directly.
So that's this announcement.
If you're calling from your home phone number, press 1. If not, press 2.
Okay, so that's this routine.
Please hold while we access your account.
So now we go get your bill.
If you're calling to make payment arrangements or if your service has
So
been
now you're here
disconnected and you need
at the main menu.
information, press 1. For all other inquiries, press 2. This is the main menu. For information about miscellaneous charges such as usage minimum, universal connectivity charge, or carrier line charge.
These are all the questions that people call up and ask. So this has to get changed, you know, on a weekly basis to keep up with the world.
For local call service, also known as in-state or regional long-distance calls, press 3. For information about the AT&T website and internet service, press 4. To hear
And this goes on and on.
again, press 7.
Don't fall asleep on me, Fred. It'll be done soon. I'm bringing back memories of his lunch table.
Here is a summary of your account information.
Okay.
As of March 13th, 2000, the balance due on your account is $525.54.
So for those of you who don't have teenagers, that's what you have to look forward to.
On your account since your last bill on February 25th, 2000.
Okay. So to avoid the menus, they just play you some information. So now we're finally down here.
To call on your bill, press 1.
So that's actually the option that you want.
For a call on your bill, press 2. For rate information, press 3. To hear about or enroll in an optional calling plan, press 4. For calling card and other commonly called AT&T numbers, press 5. For payment and billing information,
So everybody had enough?
press 6.
Okay. So the idea is that there's this large collection of things that are some stationary, some changing. And in order to avoid having to charge people $5 or $6, telephone companies, banks, the IRS, the Social Security Agency, insurance companies, you name it, spend, dozens of user interface people. These are people with PhDs in psychology from, all sorts of high-class places to design things like this and to keep track of it on an ongoing basis. It's amazing. I won't tell you what the percentages are of how many people actually manage to find their way through these things. Not all that many. What's happening if I can just say, how may I help you? And then we get this.
AT&T, how may I help you?
Yeah, there's this charge on my bill. I don't think I made this call.
Are you calling from your home phone?
Yes?
Please hold while I transfer your call.
Okay, and now we're immediately here.
Please enter the area code and phone number you don't recognize.
Okay, and that's in the IVR submenu. So the idea is it takes this whole big complicated hierarchical tree and it flattens it out. Okay, so it's far superior from everybody's point of view. People, we find, would rather either get to the automation immediately, or if they need a person, get put on hold and listen to music, than have to spend minutes doing something interactive and horrible and trying to sort out the mess. Okay?
I wish they did a button cut out. Because if I'm waiting, I'd like to work. I don't want to be disturbed by your music.
We'll put in a special bargain feature that says shut up.
Yeah.
Okay? And very, very, very reasonable. Very reasonable. Okay, so that's the domain that they asked us to look at it, and that's the value of it anecdotally, both from our perspective and the customer's perspective. So now let me go on and talk about the complexity of this task and some attempts that we've made to quantify this complexity. Okay, so one thing, if those of you who remember my list of 15 call type labels from the operator world, and then we also looked for things like phone numbers and card numbers, which are named entities, if you will. In customer care, there are 19. I didn't list them all. And some of them are very concrete, like I have a question about my account balance, or about my rate calling plan, or how come I'm getting billed every 3 months. Andreas, question?
This is based on some statistical, this is chosen based on some statistical basis, so this is, you pick these 19 classes.
The people who run the channel gave us these 19 classes. Okay? So they told us it was easier than us trying to figure it out. Now, what I want to point out is some of these are very concrete questions where the machine will actually do something. Others, like I have a question about my bill, the top one, is sort of a non-terminal. Right? So you have relationships like asking for my account balance is a kind of question about my bill. Saying that I have an unrecognized number is a kind of question about my bill. It's also a kind of question about a charge on my bill. Okay, so you have is a kind of relationships amongst these things. When we look at the named entities over on the right that appear, people say item number 4, on page 7 for $1.98. What the heck is that? Okay, so these named entities show up in their speech, And there are a dozen of those. And what happens is when you have a question about an unrecognized number on your bill, well, I need to know who you are, what your home phone number is. Okay, I need to know which bill. I need to know what the dialed number was so I can tell you who it belonged to. So these call types have a named entity as an attribute. So these is a kind of and have a relationships amongst these things. Okay, for the computer scientists in the audience, the bells that say object-oriented relationships and hierarchies should be ringing. Okay, and Alicia Bella, who works on dialogue in our lab, actually introduced the notion of creating a object-oriented representation amongst these things to make explicit these relationships. Now, let me spend a second about that. So it's not merely a list. If you think about it as a classifier, then it's just a list. It is the structured object, and the question is how to use the structured object. Let me compare for you the graph representation of these relationships from the operator world and the customer care world. Okay? So in the operator world, all the stuff that's in all caps are what we used to call call types. So questions about time, rate, directory, area code, were all kinds of queries about information. Okay? Things like collect and calling card and third number are a kind of billing method. If you're making a call has a billing method. It also has a number that you're dialing and optionally has an attribute of person to person, which I don't think anybody uses anymore. And something like a phone number, well, a phone number is a forward number, but it could also be the number that you misdialed that you want a credit for. Okay, so it's not even a tree. So this is the task structure graph that represents the relationships in the operator world. For the customer care world, it looks like that. And you're not supposed to be able to read it. And this is a draft. And the point is, gee, that's a lot more complicated. So there's a lot more nodes, there's a lot more arcs, there's a lot more relationships. There are some theories floating around about object-oriented complexity, which I don't fully understand yet, that we're trying to understand how it fits in here. And somehow having these constraints, even though it makes the model more complex, should make the decision process simpler because the model gives you some amount of information. Right? So that's one set of ways of looking at complexity. Another easier, more familiar way of looking at complexity is up here for customer care. I say, let me take those 19 call types that I listed, let me forget about any relationships amongst them, and let me plot them in rank frequency order. Okay? And what we get is the skewed distribution that goes like this. The entropy of that is about 3.3. All right? And one of the gotchas here is that other is about a quarter of the data. So even though they gave us those 19 call types, there was this big chunk that wasn't on the list. And when you look at the other, and you sort of say, well, gee, you could have had a call type for this, and you could have had an IVR menu for that, and you could have had another IVR menu for that. And we said, well, why didn't you put it in? They said, well, nobody could find what was there now. So why should we? So that's why we didn't put them in. But once we flatten everything, then we can put it in. Okay, so the open set component is quite large in its current incarnation. Comparing this to the operator services world, which had 15 call types, the entropy of that distribution was about 3.1 test set. Okay, and there's a unigram entropy. So you go, gee, not terribly different. But one of the issues here is that the other set component, the tail of the distribution for operator services, was only about 12%. And if you tried to pick anything more off that, you'd get a 0.5% at the time. So you were pretty much done. So while this is a reasonable way of characterizing the semantic complexity, what I'm not quite sure of is the semantic complexity, this entropy, doesn't include the fact that the open class component is a lot bigger, and what impact does that have, and how do I understand that issue? We tend not to think of entropy in terms of open class problems, but more in terms of closed class problems. Anybody has any thoughts on that? I'd love to hear about it. Another question that you can ask is, well, this complexity is reflected in the language. So while the top chart for customer care, people talking to people, there was an average of 39 words per utterance, a lot. Down in the operator world, it was only 19.
That means one turn in the dialogue?
Yes, and this is in a dialogue between a person and a person.
And that's one turn?
That's one turn.
Is that, but there may be many turns.
And there may be
so
many
that
turns.
is still effective.
That's right. Yeah, and things change as you go down. Right? So this says that these sentences are a lot longer. And another way of looking at it, which again characterizes the open class component, is if you look at the vocabulary growth as you go through the training sentences. So if we take an equal amount of 8,000 training sentences for each domain, operator services, by the time you get out to 8,000 sentences, we're at 3,600 words of vocabulary. Customer care, it's more like 5,400 words. The perplexity trigram test set is more than double. So more words this way, more words as far as variability makes sense. Okay. What's interesting is that the slope of these curves, which is the open set component, the added vocabulary per sentence rate, seem to be roughly equal. That's kind of interesting. Okay. Okay, let me try and summarize the ways in which we can quantify these complexities. The vocabulary and the perplexities of the language in the new task are about double. The utterances are twice as long. One of the problems that leads to is we get spurious and misleading salient fragments. You know, the longer it goes, the greater the probability of false detection. The open set component is double. Something that I didn't mention before is that 12% of the requests in customer care actually get more than one semantic label. That almost never happens in operator services. Maybe some tiny percent of the time you get people wanting to make a collect person-to-person call, you know, but it's down in the 1% region. Here you get a lot more multiplicity. There's this business about the task structure graph being much more complex, roughly double the number of nodes and arcs in the semantic representation. And Alicia, my colleague who works on dialogue, made me add that last bullet, which says not only do you have to figure out what people want, but you have to figure out who they are too, which adds another dimension to the problem.
Why do you need to know who they are?
It actually depends on what question you're asking. If you're asking, what is this usage minimum charge, then we'll play you a little blurb, and I don't care who you are. If you say, there's this unrecognized number on my June bill, well, I have to know who you are so I can look it up on your bill, and if you want a credit, to give you the credit as opposed to somebody else. So that's part of the system. Okay, some experimental results. The architecture that we use, okay, which should look familiar in some of its parts, is the person talks, we have a speech recognizer, we have acoustic models and language models, okay, standard stuff. The spoken language understanding uses the salient grammar fragments that I talked about before, okay, of which there are a few hundred, searches for them, and since it's not just a classification, if it was a classification, it would generate a probability distribution over the call types. What this actually does is generate a probability distribution over that graph. Okay, so this is the work of Jerry Wright. So what we do basically is say, let's first treat it as a classification problem, mapping the detected salient fragments onto a probability distribution over the nodes in that graph, and then run a propagation algorithm which sort of does inferences and redistributes the probabilities, taking into account all these relationships. So for example, if somebody dialed a number when I said, how may I help you, and touch-toned, well, the fact that I have a forward number, that triggers the fact that they want to make a call, and that's the graph propagation algorithm. We then send that probability distribution over the graph to the dialogue manager, okay, which looks at it, does a variety of things that I'm not going to talk about today, and does two things. It decides what's going on, does various thresholding and so on, and then decides what question it needs to ask the user and generates a prompt. And the prompt might be something like, okay, so are you calling from your home phone? I know what you want, what's going on with it. Or it might be, do you have a question about your June bill, about a number that you don't recognize? A confirmation or a clarification. So the other thing that the dialogue manager has to do is send back a context to the spoken language understanding that helps it to interpret what's going on next. So if I ask the yes/no question, it needs to know that sort of thing. So let me show you an example here. This is a transcription of something that somebody said. Below is the ASR output. I'm going to play you the audio file so you don't have to do it yourself. But just let me tell you what you're seeing here. Wherever it made a recognition error, I turned it gray a little bit. Okay, word accuracy here is about 65%, like in switchboard or things like that. The things that are highlighted in color, like wireless phone and 7 cents a minute and one rate plan, those are matches with the salient grammar fragments. Okay, the reds point towards rate calling plan type of question, and wireless phone points towards questions about wireless phones. Okay, so let's listen to the audio and follow along with the recognition. And what's interesting is you can see the recognizer does make mistakes, but as was pointed out in several conversations this afternoon, it tends to make fewer mistakes on the salient words than it does on the non-salient words.
Okay, I got AT&T wireless phones. Yep. And when I got them, he told me that I would be switched to 7 cents a minute for all my AT&T long distance phones, because I was on 10 cents one rate plan.
Okay, so that's the recognizer output. And somebody wanted to call it a semantic parser. I don't know if it fits into that exactly, but the algorithm that we use to make the decision asks several sorts of questions. One is, how strong are the associations between the detected fragments and the various call types? The second question that it asks is, how many words does it cover? So a longer fragment with more syllables in it counts more than a shorter fragment. There's more words involved. Okay, the other thing that it asks is, what is the acoustic confidence, the utterance verification score of that salient fragment? Okay, and when it puts it all together, it says, oh, these longer guys that are more strongly associated win, and we're going to have a conversation about rates and calling plan. And I'll send you to that submenu. Okay. If you look at call type classification on this, we measure two things traditionally. So this is a multi-class plus rejection. We ask, one, what is the false rejection rate? False rejection means you came in, you asked me a question, it was about something on my list, and the machine said, I don't know, sent you to a person. So that's an error, but the cost of such an error is a missed opportunity for automation. Customer doesn't mind, we might mind a little bit. So even though I'd like to sort of never miss anybody who wants something on my list, I'd like that false reject rate to be 0. Even if it's 40 or 50%, then I'm trying to automate the other 40 or 50%, which is pretty good because 50% if it got zillion calls is still a lot of calls. Right? The other thing that we measure is the probability correct. So given that the machine thinks that it knows what you want, is it right? Okay, and that better be pretty high because we're going to have a dialogue to correct or clarify any mistakes. Okay, and what I have here, and these are experiments, batch mode experiments on classification from the speech of people talking to people, trained on 10,000, tested on a separate 1,000. Okay, and let's see. The text curves are the guys with the circles. So this is the rank 1 text curve. Okay, so this says if I took the transcriptions, if I had a perfect recognizer that got every single word right, and I did this classification, and you can trade off one of these errors against the other. How? By saying you have to be this confident, otherwise reject. Change that threshold to here, you reject more, hopefully you do better on the rest, right? So you sweep out an ROC curve. So this is the ROC curve for transcriptions rank 1. When we go to speech, it drops a few percentage points. And one of the things that's kind of remarkable to me is when you say, well, how much did it drop? Less than 5 points, right? So that the understanding rate only drops 4 or 5 percentage points when I move from text to speech. What's the word accuracy? The word accuracy is about 65% on tasks like this. So even though I'm only getting right 2 words out of 3 from the ASR point of view, there's only a 5% differential in the understanding task. And that's pretty remarkable. Okay, I think that's kind of neat. And it shows you that we're extracting those 3 bits pretty well, while word recognition accuracy is asking you to extract hundreds of bits as opposed to 3 bits. Yeah.
Do you threshold the output of the speech recognition? In other words, are you taking one best?
In these experiments, we're taking one best. We've done other experiments with lattices.
Right. How much do throwing in the lattices get you back on this?
We actually haven't done those experiments with this data yet, basically lack of time. We did those experiments actually with phone-based classification work that we had done, where we were acquiring salient grammar fragments built up out of phones to see how well we can do if we had no transcription. And we had a paper in ICSLP that reported on how much of an improvement you got in that kind of task, moving from best path to lattices. And the same thing ought to work here. We just haven't gotten to it yet. Okay? It should buy a lot. Okay?
I think part of the question about, the real question is why it is that you're not hurt by this. And it could be,
Well, you're,
the real question is why the damage word error rate doesn't hurt your classification very much. And there are a few possible explanations. So one obvious one is that you recognize the content words that really matter. Another is that you recognize enough of them, and you're likely to get at least one good trigger, or the good triggers are
yeah, and actually,
all the bad ones.
yeah, actually both of those statements are true. What we've shown,
I see you have broken it down.
yeah, in other words, not on this domain, but on the previous domains,
Yes.
what we've shown is that, and other people have shown too, is that the word accuracy on the salient words is far higher than on the non-salient words. And, you know, I can even show you a correlation plot.
Because of length?
Why? I don't know. There's just an empirical observation. So what we like to say there is that whoever designed natural language did a good job and made the salient stuff easy to recognize. Factor analysis is another question.
Isn't that against our 95 results that, in fact, the short words are recognized as well as the long words? And we attributed it to the fact that words like the, etc., are so frequent in the training corpus that we have a much better model for
That could be, yeah.
In other words, we had a result at the 95 workshop, summer workshop, that function words were recognized as well.
Yeah, right, often better.
As the
Yeah,
content words.
but a distinction that's important to make is between the, you know, things like the length or something a function word or not, which is a
Maybe
sort of
the point
syntactic
is that
issue.
the salient words that you call are frequent enough, while content words trail off, and maybe you don't. In other words, they have a high enough language model probability in your case, and furthermore, you see them enough in your data so that you have them well.
Right, right. You get those.
The
Yeah.
acoustic model.
Right. What we also found in some sort of minor experiments was that the context of the salient words tends to be much more restricted than the context of non-salient words. So, you know, if you look at sort of the left and right branching factors around a word like collect, it's very small compared to the average branching factor.
The biggest predictor for recognition errors was backing off the language model.
Okay, so that would indeed do it. And, you know, there are interesting relationships that you can explore empirically and analytically between the information content of a word for the task and the information of a word as related to its language model, perplexity. And there are relationships, but they're not the same. Okay? So I think that's a whole interesting question. And what are all the factors that go into this? You know, a lot of work to be done and understood, and I'd like to do that more. Now, the top set of curves are the rank 2 curves for speech and text. What do you care about? First, what is rank 2? Rank 2 is, if you think about it as a classifier, says, oh, is the right answer within the top 2? Okay. And you say, well, why would that be interesting? If you got it wrong, you got it wrong, right? And the answer is no, you have a dialogue system. If you tell the dialogue system, hey, it's either A or B, but nothing else, but I'm really not sure which one, you know, and it's 70-30, A and B, well, the dialogue manager can come along and say, did you want A or B? Or did you want A? No, then it must be B. So, you know, just as a single stage process, the understanding component is trying to extract bits from the utterance. The dialogue manager is also trying to extract extra bits from the utterance, okay, and to ask the right questions to clarify that stuff. So the rank 2 performance tends to be much more predictive of dialogue level performance. So what I want to do now is to play you some examples, and a comment that I made to several people earlier is we took all this data that we collected from both human-human, which is what I talked about today. We ran several months of wizard experiments, which, you know, is people think they're interacting with a machine, but you have somebody pulling the levers for the non-speech people. So pay no attention to that man behind the curtain. Collected a lot of data, and we actually went live about 3 weeks ago. All right. So and AT&T is going to issue a press release, which is nice, sometime before the end of the year. I have a draft in my briefcase, which I can't show you. But we're actually handling live calls. Right now it's running just 9 to 5 every day on a small number of channels. Everybody's very happy with it. I listen to it. I find all these things wrong with it. And they tell me I'm its worst critic. But the people who have been deploying those wonderful menu systems that you heard for years just sit there and go, this is great, this is wonderful, and it should be ramped up nationwide end of next year, you know, third quarter next year. So let me play you some dialogues. Okay, and one of the things that you'll hear in these dialogues is that people don't get to the point all the time, and that part of what the dialogue manager has to do is, oh, you have a question about your bill? What kind of question? Or if somebody says, what are you? You have to answer that question too, all right? So let's try one.
AT&T, how may I help you?
I have some charges on my bill.
Okay, which charge are you calling about?
I'm supposed to be getting 10 cents a minute, and they're charging me 12 cents a minute.
I can help you with that. Are you calling from your home phone?
Yes.
I'm accessing your account. Please hold while I transfer your call.
Okay, so now we transfer into the existing menu system.
This is the rates and calling plans menu. There are 6 options.
Okay, one comment from one of our VPs was, you know, there's this jarring discontinuity between how may I help you in these menus, right? Can't you apply it to those 6 options too? And we said, sure. So that's a project for next year. Okay, so.
You really know how to hurt the guy. I mean, this guy is already happy that everything is going.
Such is life. Well, that's why we have to do the rest.
It's like calling customer service anywhere else. They just keep transferring you to someone less confident.
Okay. Some things work better. Okay. Here's an account balance question.
AT&T, how may I help you?
I'm calling about a bill I received this morning.
Okay, what is your question?
I sent on
being charged for last month's balance, and I set the check in August 1st. And so they combined that balance and this month. I've already set the check in. I sent it in August 1st, and I just wondered why it wasn't noted.
I can help you with that.
Okay, so, and I
Go back to the menu now.
I actually cut out the rest of it because then it asks her for her phone number, and she actually gives you her phone number, and I can't play that. You wouldn't call her? I know, but there are federal privacy regulations. Yeah. Okay. Here's one where somebody's calling about a local service question for which there is no automation, and we send you to a rep and pop up on the rep's screen the fact that you're calling about local.
AT&T. How may I help you?
Good afternoon. About 2 months ago, for some unknown reason, my long distance charges came out with AT&T. Okay? Am I talking to a person or a recording?
You are talking to an AT&T automated assistant. You can speak naturally to me. Just briefly tell me what I can do to help you.
Okay.
Okay.
Can I get my regular?
Is that amazing? I didn't think that was going to work. When the user interface folks told me they were going to do that, I said, people are going to hang up on you. That was the typical reaction. Okay, like 98% of the time, it was really, people just said, okay, and they kept on talking. And I said, they've been watching too many science fiction movies, right? But it makes it work, okay? Now, one of the questions that came up in our experiments was a small but significant fraction of the people who called started talking and then said, what is this thing? Some people never noticed it was a machine. Some people knew it was a machine, talked to it slowly, like you heard. And a small percentage said, what is this? Who are you? And we explained it to them, and then they recovered and they went on. So to me, that was fine. Somebody asked me the question earlier, did we check with the customers? Well, there were surveys done. We called up customers, a random sample, after they spoke to it, and said, how did you feel about this? And got feedback. This is what the marketing people do for a living. And for the small subset, they said, most people were fine, but the small subset said, gee, I was a little uncomfortable there for, one term. So the user interface folks said, fine, let's do some experiments and see, can we be more explicit in the first prompt? And there's a trade-off between being really, really, really explicit and annoying everybody with it versus being a little explicit so that it's not very annoying or doesn't bother the general population, and for that small fraction gives them time to acclimate and avoid what we call the deer in the headlights syndrome of freeze, right? So we actually moved on and changed the prompt and the user interface a little bit.
AT&T. I am an AT&T automated assistant. You can speak naturally to me. How may I help you?
Yeah, I've got questions on my billing.
Okay. What is your question?
I've got 5 charges on my long distance that were in August, and I don't know who they are or what they are.
I can help you with that. Are you calling from your home phone?
Yes.
Please hold while I transfer you to the billing system.
Okay, so that was a slightly different user interface, and it turned out not to affect the completion rates at the dialogue level very much, but just to do away with that little bit of discomfort that some people had at the beginning, and the prediction is within a year, we'll go back to the old one because everybody will know about it at this point. People don't know about it. Yeah.
People likely give you all this information and then you forget it because you ran into another person who had no history of previous dialogue?
Actually, not. Okay, again, to my surprise, one of the things that we measured was if you go through this dialogue and it turns out, for example, that it's something that can't involve automation, and I'm going to transfer you to a rep. After I send you to the rep and I look at the statistics of how long you talk to that person with no memory. Okay, that person knows nothing about what you called about. It is significantly shorter conversation than it is in the general traffic. Okay, and we did a whole bunch of factor analyses on that, and I can't quote you the exact numbers because I'm not permitted to, but it was significant and major. And our conjecture is that part of what it was doing was helping you to formulate your thoughts. Okay, so there was a payoff there for both sides. Now, something that we should and will do is have some sort of memory. So even if we transfer you to a person, okay, we'd like to take the audio file, you know, of what you just said. If it's short enough, ship it over. If not, the ASR output even, and ship it over. This way the rep can look at the screen and see roughly what went on, okay, and then continue the conversation with you. And that kind of thing seems very reasonable, and there's machinery to do that. It just has to get built.
I have Chase Pay by phone, and they irritate me this way all the time. When I call them, they ask me to put in my account number,
right,
etc. Then they transfer me to a guy who talks to me.
Who totally
he
forgot
asks
it.
me for the goddamn account number.
Right, very annoying, very annoying.
All right.
Yeah.
And
Yeah.
they even, you know, I even dial, I mean, I punch it in the account
Right.
number. There's no reason why it shouldn't appear
Exactly.
on the screen.
Yeah, that's right. And one of the things that happens with all these systems, you know, as I've gotten to talk to these people, is there are multiple things wrong with them. These big messy menus are just one thing that's wrong. There's lots of other issues like that which also need to be addressed. And, you know, that's definitely true. Now, let me just show you very, very briefly what happens when you think about the dialogue and what happened. So this is a particular granularity dialogue trajectory. Okay?
A particular what?
No, it's a dialogue trajectory, but picking a particular granularity for the state space.
Yes, yes.
Okay? So there's no explicit notion of state in the dialogue manager, but one can impose it a posteriori. So what we did was we said, well, after we said, how may I help you, people responded. Sometimes they said nothing, and we had a reprompt. Sometimes they said something like good morning or afternoon or how are you today? Or hi, my name is Joe, and we had a reprompt. A little bit of the time they hung up, which is actually a typical kind of statistic. And then these two big flows, this one here, 58% of the time, they said something specific enough to me that I was able to figure out what they wanted. And we were done with the what you want part of the conversation. 27% of the time, they said something like, I have a question about my bill, in which case we have to move to get another couple of bits, clarification. What kind of question about your bill? Now, most of the time they say, well, there's a number I don't recognize, and you're done. Sometimes they say, I have a question about this funny charge on my bill, in which case you go back and you say, what kind of funny charge on your bill? And then they say this call to Baltimore, and I don't know anybody in Baltimore.
So do you repeat what they say? I mean, are you like Eliza?
Not quite that good yet, okay? But to a certain extent, we do certain recognition of dominant dialogue acts and repeat them back. So the interesting thing here is the ratio of specific to vague, which is about 2 to 1 there, okay? If you look at what happens after the reprompt, specific to vague is more like 3 to 1, okay, because they've gotten more comfortable with the thing and they know what they're talking about. So one can do trajectory analyses like this, and something that's interesting is you can look at this as sort of the mode or the mean of the dialogue trajectories. You know, if you think about some system that spit out a single number at the end of it, well, I'd measure its mean, I'd measure its standard deviation, and I'd say, what's the mean plus or minus 3 sigma? If something fell out of the mean, you know, plus or minus 3 sigma, then I would tag it red and go look at it if I was in a chemical plant or a chip manufacturing plant. You can do the same sort of thing here. There are all these other little tiny things which I pruned using FSM prune. Okay. And one can actually do what we call problematic dialogue recognition. What are some of the weird dialogues? Well, remember, this thing's just busy chugging along. You can't listen to all these things. Can I have automated procedures, like in a control system, to go through, automatically identify those atypical anomalous dialogues which lie 3 sigma outside the mean in some new sense, and examine those by hand. Okay, let me close with mentioning some related research topics. The talk that I gave in Colorado last year where you couldn't get near the poster, which I promised you a talk on, I didn't give today, but that's on work that we did on how can we exploit speech without transcription. Why would you be interested in that? Well, you know, we transcribed the first 10,000, we transcribed the next 25,000. We have people coming along asking us to do a new task. Transcription is a bear, okay? Anybody who works in speech knows that. If I'm taking millions of calls, what am I going to do with it? If I want to do a dozen tasks at once, what can I do with it? So we did a bunch of experiments that said, if I started out with the speech alone without transcription, what can I learn? Well, if you just asked that question, that would be saying, what can you learn by listening to the radio? And you can learn some things, but not a heck of a lot. But if I say, aha, I'm going to give you the speech plus the semantic tag, plus the call type, and that can come from a wizard clicking, it can come from the dialogue itself, after I ask confirming questions. What could you learn from that? And what we did was we ran a task-independent phone recognizer over it, got, you know, phone output, which was right 40% of the time, which is what phone recognizers do, and then said, let's apply the salient grammar fragment analyses to build up salient grammar fragments of phones, which we can then use for classification. And you can actually do quite well. Okay, and exploiting lattices lets you do even better, which was an ICSLP paper that we have. This whole issue of problematic dialogue recognition, we would much rather the machine know when things are going badly than the person tell us by hanging up. That's bad for business. So Lynn Walker and Jerry Wright and others have done some work separate from what I just described on what are predictors of a dialogue going well or badly, and if it's going badly or diverging, we should either change our strategy or bail out to a person. The whole issue of doing this for multilingual systems, Srini Bangalore and Beppe Riccardi have reported on results for Spanish and Japanese and Chinese, and we actually have a Spanish version of the How May I Help You system for operator services running in our lab. And you know, extensions of that early work that I did with Nans Shankar to multimodal systems, I continued with Deb Roy, who's up at the MIT Media Lab and was a student of Alex Pentland and is now on the faculty there. So that's what's going on. Thank you very much. Questions, more questions. We had plenty of questions so far. Hi. Sure. Yeah, very briefly, the idea is just as you can talk about associations between what you say and what you want, okay, which is a mutual information, and people who do statistical language modeling talk about what are the associations between what you say and what you just said and what you're going to say next, which is the same mathematics. You can also say that if I'm in a multimodal environment and I'm looking at things, what are the associations between what I see and what I say? So for example, if I asked you the meaning of the word red and you were blind or colorblind, the meaning of the word red would be very different to you than it is to me. And just as we can do clustering in the joint space of what you said and what you want, you can also do joint clustering in the audio and visual space. Okay, and Deb, you know, explored this set of ideas for his PhD thesis, actually compared the way his little robotic bird that he called Toko learned about colored blocks and shapes, which extended Anand Shankar's earlier work, which was purely graphical. And then went a step further, and he had gotten a query from somebody who had read one of his internet articles, who was doing research in how infants acquire language at the University of Toronto. So they started a correspondence. He extended his thesis to compare how his bird was learning language to how infants acquire language. And that collaboration became quite intense, and they got married in August. Okay. And Deb is now on the faculty under Alex Pentland at the Media Lab and continuing these ideas. And he finally just sent me a draft last week of a speech paper. He's given multimedia, and multimodal papers on it, but I was pushing him to write something for the speech community, and there's a draft, and there'll be a publicly available draft by next month. Okay.
How does the routing accuracy compare when you take phone lattices directly as opposed to a recognizer output?
Mm-hmm. Yeah, the answer to that one, so if you say, okay, if I started with no transcription and just built up these units from phones, how well could we do? And if you look in the ICSLP paper, there are the details. Basically what happens is you do worse than if you had transcriptions, but you get operating points like 90-something% accuracy at 40% rejection rate. So what that tells you that if you had a wizard clicking away for a week and the stuff was piling up on disk and all of my transcribers were busy, at the end of the week, the system, based on these bootstrapping techniques, with never a transcriber, would be attempting half the calls on its own and getting the right answer 90% of the time. Now that's not deployable in any sense, but that's really rather remarkable, and we can do a lot better. And then you can imagine all sorts of ways of bootstrapping it. So, example, Beppe Riccardi had a paper at ICSLP that said if you take these acoustic morphemes that we find, these phone sequences, and if they happen to match a dictionary pronunciation of a word in English, say bingo, and then use that to estimate the unigram statistics of that word in the new corpus, again with never a transcription, and you get major results that way. So there's all sorts of things that you can do. That's something that we consider a rather far out question, but given that we're going to want to do this for more than just this one task, and that we're already getting more data than we can possibly transcribe, what do? How do you exploit what you can't transcribe? How could you automatically look at the speech? And instead of doing what we do now, which is just say take every 10th transaction and ship it to the labelers, because that's all they can handle, and soon it'll be every 100th transaction, every 1000th transaction. Is there any more intelligent way of picking out which ones they should look at and label? So that's part of that whole broader theme. Okay. We can talk a lot more about that one. Okay. Thank you.